All right, welcome to chapter 8. This is part 1. So, we are going to go through stoichiometry, which is a big scary word, but I promise you that you already know a lot of the stuff I'm going to show you in this video. So, essentially, why would we even care? This is a great example of why we would care. Chemical reactions produce products that maybe are not ones we want. For example, this octane, you can tell by the 8 carbons here that's in your gasoline combusts. We should recognize this as a combustion reaction from your work in chapter 7, and it makes carbon dioxide and water. The water is vapor, and see if you can think of why that would be here. And this is called a complete combustion, and not all combustion reactions have exactly just these products. There's lots of other what we call intermediate products or byproducts where you get this soot. It kind of depends on is how good your engine is. If it makes only carbon dioxide, that's pretty good. But you may know that in dense cities where there's a lot of automobile traffic, we have a lot of carbon monoxide. We get a lot of other kind of carbon compounds and things that maybe aren't so great for us to breathe in and also aren't so great for the environment. But what stoichiometry does is it tells me that if I burn some amount of gasoline, assuming gasoline's 100% octane, which it's not, but if I burn a certain amount of octane, how much carbon dioxide will I produce? And so this is a very really reasonable question to ask. And in science and in chemistry especially, you want to know how much you need of a reactant to get a certain desired amount of products, or um, you find an amount of products from your reaction and you work it backwards to figure out how much reactant you must have had in that reaction. So it's very, very helpful what we're going to show you today as far as stoichiometry goes. So what is this word I keep saying, stoichiometry? Stoichiometry is just a relationship between all the things in a chemical reaction. You already have been thinking about these things probably in your chapter 6 and chapter 7 work, in your moles and reactions work, and we're just going to now combine all the conversions you've learned, the mole conversions, with your chemical and balanced chemical reactions. So it is predictive in nature. It also exploratory. You can explore natural reactions as well and figure out what's going on. But before we get into the chemistry of this, let me just reassure you that you actually already do this. You already explore the relationships between these things. If you've ever baked something and you've had to modify the recipe, you've done stoichiometry essentially. It's the same idea. So a recipe is kind of like the same thing as a chemical reaction. So take this recipe, for example, flour, eggs, baking powder, pancakes. So if I were to put 1 cup of flour, 2 eggs, half a tablespoon of baking powder, I'll get 5 pancakes according to this reaction. Okay, so this is kind of like our chemical reaction. Right? According to the one run of reaction, the product is going to be 5 pancakes here. But let's assume that maybe I don't have exactly 2 eggs. Let's say I want to make as many pancakes as possible and I've got 8 eggs. So if I have 8 eggs, how many pancakes can I make? Assuming I have enough of every other ingredient. So why don't you pause and see if you can figure this out. So maybe you wrote something down. Maybe you didn't write something down. That's okay. If you did this in your head, well, how easy was that? If you had to write something down, that's fine. We do this math all the time. So you can think about what's the relationship between 2 eggs and 5 pancakes, and how can I make that the relationship between 8 eggs and X number of pancakes. Now, you know that I'm going to tell you how to do these conversions with dimensional analysis, and that's really what I want to see in this class, y'all. So in this introductory chemistry class, I really need to see you solving the problem using dimensional analysis, because it's the way in chemistry that we track our work, that we show we know what we're talking about. Just doing some mental math, some ratio math, it can give me the right answer, but it really doesn't show that I understand the chemical relationships between things. So make sure that you are able to turn even a simple question like this into a dimensional analysis problem. Notice here that I have gotten rid of my egg unit by putting the eggs in the bottom. So 2 eggs from my recipe and 5 pancakes, that's from my recipe. So this is the ratio from my recipe. I've applied it to the amount of eggs I want to use, and I pop out the amount of pancakes that many eggs would give me. So that is stoichiometry right there, and it should look very familiar to you because it is in fact a mole conversion, a mole ratio, which you already know how to do. We're just going to add it into now reactions. So instead of talking about, for example, 3 hydrogens in 1 ammonia molecule, we're going to start talking about 3 hydrogen molecules plus 1 nitrogen molecule produces, or yields 2 ammonia molecules. So these numbers in front are called coefficients. And they are not subscripts, they're different than subscripts, but we can use them just like we use subscripts to give ourselves a mole ratio. So how could I write some of these ratios? So let's look. I could absolutely talk in terms of molecules. Okay, isn't it true that 3 hydrogen molecules is in a relationship, in a ratio with 1 nitrogen molecule? Again, I'm just pulling these coefficients down into this ratio, and it makes 2 ammonia molecules. But when are you ever dealing with only a number, a handful of molecules? They're so tiny. So the unit of atoms and molecules isn't really helpful for us because we don't really deal with individual little molecules and atoms. We deal with large packets of them, and thankfully, we have a unit that helps us deal with those packages. Moles help us deal with these packages. So notice that my numbers stay the same, but because Avogadro's number works the same on all of these, I can just replace the molecules with moles and have the same ratio. It's beautiful, wonderful, and it allows me to do a lot more quick math than having to go through Avogadro's number every single time just by looking at a chemical reaction. So you can assume that the unit for your coefficients in your chemical reaction is moles. So make sure that you're using the unit of mole when you're talking about mole ratios. Don't tell me 3H2 is equal to or in a ratio with 1N2. This doesn't have a unit, and I really need a unit for me to be able to know how to use it mathematically. If I don't have a unit, how do I know what to cancel? How do I know what to bring out? So make sure that you're utilizing the unit here as well as the substance, because now the unit is the same for all of these conversions. So you need to be specific about what substance you're talking about. So how would I use this? So let's do a practice problem. If I have 3 moles of nitrogen and more than enough hydrogen, how much ammonia can I make? Give me the moles of ammonia. Okay, go ahead and pause and work it out. Hopefully you have done that. So let's look. If I'm thinking back, maybe you're a fan of the trigger chart that I showed you in chapter 6. So I'm looking at, I don't see any mass, so I don't need molar mass. They're not giving me information about mass. They're giving me information about moles. They're asking me about moles, so I don't need molar mass of ammonia. But I do have 2 different substances. So nitrogen and ammonia are 2 different things, and that means I need a mole to mole ratio. We're going to ignore the hydrogen because they tell me, hey, you got plenty of hydrogen. Don't worry about it. What's going to limit my reaction, we'll come back to what's called a limiting reactant later, is going to be my nitrogen. So how can I start this? Well, if I know I need, let's see, my given information, my starting place is going to be my 3 moles of nitrogen. My unknown is going to be how many moles of ammonia. Remember, ammonium is an ion, so this is ammonia. And then let's look at a conversion that we may need for this. We only need one conversion. It is a mole ratio. So make sure that you know the names of some of these conversions because it's going to be helpful in your communicating with each other. What is the mole ratio I need? Well, I need the relationship between nitrogen and ammonia. I do not care about that hydrogen. If you know you need a mole ratio, just go ahead and write blank mole of the first thing equals blank mole of the second thing. Then later, once you've written all this stuff out, you can then use your brain and go back and put in these numbers. Where do I get the numbers from? I get the numbers from the chemical equation. And guess what? It's got to be a balanced chemical equation, or you cannot use these numbers. So we're now building on our work in reactions in chapter 7. So here's my mole ratio. Let's check to see that I have all my conversion factors. And this is a very helpful thing to do as you add on more complicated conversions to go back to the basics and write out my given, write out your unknown, write out your conversions as an equality, and then make sure you can go from one to the other. So if I start with moles of nitrogen take me to moles of ammonia. Moles of ammonia are what I want. I don't need to write any more conversions. I don't need molar mass. I don't need Avogadro's number. So if I start with 3 moles of nitrogen, I can say for every 1 mole of nitrogen, there are 2 moles of ammonia. And hopefully, this is your happy place. If you can sit down and do some conversions, you feel comfortable and confident in that place. If it's not quite your happy place yet, you need to do more practice with it. So we're going to keep building on this. So you don't really have to have a calculator to do this, but if you want to check, it's never a bad idea to check with your calculator. I'm terrible at mental math, so I will check my calculator for the simplest things. We're going to get 6 mole of ammonia as our answer to this question. So hopefully you were able to figure that out. That's it. You did stoichiometry. That's all. We're going to get more complicated. We're going to add stuff on, but this is the core. Okay, this multiple ratio is the core for any time you're comparing one part of a reaction to another part of a reaction, which is all stoichiometry is just parts of reactions comparing to each other. So you will always need a mole to mole ratio. I need to see it, even if it's 1 to 1. I need to see it. I need to see the dimensional analysis and those wonderful units canceling out. So to finish off our first video in chapter 8, we're going to expand it because you already know how to do this. That's what's beautiful about these mole conversions is that you can do molar mass for single elements, or you can do molar mass for groups of molecules, and then you can apply them to mole ratios for a reaction. You've probably already done a 4-step problem before when you were doing your mole conversions practice. We're just now going to add a balanced equation as our mole ratio. No different. So this is the pattern you will see for what we call mass to mass conversions. You will use the molar mass, then you will use the mole ratio, then you will use another molar mass. And that's kind of a pattern. So those of you looking for a familiar pattern, and that's something we do in science all the time, is look for patterns. Any mass to mass conversion involving something on either side or on the same side of a chemical reaction, comparing any 2 substances. If I give you mass of one thing, ask you for mass of something else, this is going to be your path. So let's put it into practice. Now, you can absolutely, draw some things, go back to some of those mole helpful charts that I've made for you, the trigger chart and the mole maps, or use this one if you want to, but make sure that you are practicing with something enough to where you don't need one of those handouts. You don't need one of those pictures to solve problems on an exam or a quiz. Okay, let's look at this one. This is our mass to mass practice. I'm actually going to give myself a little space to work on this. Here's a nice octane reaction from the beginning of the slides. We want to know what mass of carbon dioxide is emitted by an automobile per 500, that's the same as 500 grams of pure octane used. So pause and see how far you can get. Bet you can get farther than you think. Okay, so hopefully you paused, or maybe you got stuck and you're here looking for a place to get unstuck. If you got stuck and you're watching this video, only watch it until you get unstuck. I want you to pause it again and see if you can finish the problem. Be very active with your videos, it will help you learn. So let's see. I'm going to go by the trigger chart. And if you want to use the mole map and you need some help with that, please text me or schedule a one-on-one or come to office hours and I can help you use the mole map. Personally, I'm a fan of the trigger chart because I don't have to draw pictures for that. I can just pull words. So I see that I am asked for a mass of carbon dioxide. As soon as I see mass of something, molar mass needed. Let's just write it down. So let's make ourselves a little place to put some conversions. Okay, I need a molar mass of carbon dioxide. And you know what? I'm not even going to fill the number in. I'm just going to write blank grams of carbon dioxide because I found a pattern that all molar masses are some number of grams of 1 mole of that same substance. So I'm just going to template this out and then I'll go and look at my periodic table and I'll figure those numbers out later. But you want to just write something down so that you're not staring at a blank page when you see a problem you think is going to be more complicated. Okay, so let's keep reading. Is emitted by an automobile per 500 grams pure octane. Stop. I told you before that this is octane. Now, on an examiner quiz, I will make sure that I'm pointing that out for you. But in this lecture, I told you before, hopefully you remember that a few minutes ago we talked about octane and what that was. 8 for oct. That's the compound. Also, you can narrow it down. You know what this is called, oxygen. You know this is carbon dioxide, and you know this is water. The only other thing in the reaction must be this thing with 8 carbons. So if I am telling you grams of octane, trigger molar mass of octane. And again, I'm not going to bother myself right now with plugging these numbers in quite yet. I'm going to just template it out so that I can organize my thoughts and just let the question trigger me to certain conversions. Now, there's one more trigger. I don't know if you caught it, but there's one more trigger that's a little harder to find, and it is 2 different substances. So because I literally am asking you about one thing and giving you information about a different thing, we need a mole to mole ratio, which is the core of stoichiometry. Anytime you are going from one thing to another thing in a chemical reaction, you gotta have a mole ratio. So mole ratio's template is blank mole of one thing, let's just say our CO2, is equal to blank mole of the other thing. Now, where do I get the numbers that go in the blanks for these? Because these are easy numbers to pull out. Let's go ahead and just grab them. We get these from the balanced chemical equation. So the number that goes in front of CO2 is 16 because that is exactly the number that goes in front of CO2 in my reaction. The number that goes in front of octane is 2 because that is the exact number that goes in front of it in my reaction. Don't reduce this ratio. I know some of y'all are thinking 16 to 2, that's like 8 to 1. Don't do that because if you get stuck or your dog barks in the room like happens to me all the time, you might get lost and say, wait, where did I get the 8 from? Right? Just keep it 16 to 2. Don't try to do as much thinking as you need. Just let yourself be guided by what's written there. Okay, so now let's actually, I got all of this just from reading the sentence. I haven't even sat down and decided what am I going to start with, what am I going to end with. So let's do that. So what's my given? My starting place is going to be my 5.0 times 10 to the 2, or 500 grams of octane. This is 500 with 2 sig figs. It's the only way to write 500 with 2 sig figs, so that's why they have it in this format. Okay, octane, I'm just going to write for myself C8H18 so that I'm very clear that that's what octane is. And then I want to know the mass of carbon dioxide. I can spell. So we're going to do unknown equals how many, and I didn't specify what mass. Let's spice it up and do kilo. Well, let's do grams. And then if we think the number is big, we can convert it to kilograms, right? So if I'm giving you a lot of grams, you may want to report your answer in kilograms. So sometimes in science, you will be asked to make your own decision about what unit you need to you need to represent, and it depends on the scale or the how big or how small that number is in that unit. So let's just start with grams of carbon dioxide. Okay, so let's just make sure we have our conversions before we even do the math to do our mole ratio, our molar masses. Let's make sure we need all these conversions, because you could spend a lot of time on this question getting your molar mass for each of these things and not ever need it. So before we do molar mass math, let's figure out, do we have all of our conversions? If we're going to start with grams of octane take me to moles of octane. Moles of octane take me to moles of carbon dioxide. Moles of carbon dioxide take me to mass of carbon dioxide. Mass of carbon dioxide is what I want. So if you hear me talking to myself like this, feel free to do that as you practice, or with your study group, talk to yourself and talk to each other, talk to the paper about that, which means I have all my conversions. I can now fill in my molar masses. I will let you do that. If you need a minute, pause and do that. I don't have this one memorized, but I know the molar masses for carbon and for hydrogen, so I can do a quick calculation. And again, I have things memorized to 2 digits after the decimal place, and I prefer my students to write them with 2 digits after the decimal place. Please don't round them. Give me at least 2 digits after the decimal. And the periodic table that I will provide for you on exams and quizzes is 2 digits after the decimal as well. So please do not use any other periodic tables besides those. Okay, now we can set it up. We can do my favorite part, which is my dimensional analysis. The work that we've done already, y'all, is the hardest and most important part. The work we're doing next is less important. It's the actual computation of it, but this is the good stuff. This is the science. This is where you're explaining to yourself and to others that you know what you're talking about. This is your proof here. So if you are going straight from the question to the math and you find that you're getting wrong answers and you find you're getting lost, I highly recommend that you do something to label things, something to track your knowledge. It is going to help you so much as we get more complicated with our word problems. Going straight to the math is not very helpful with a complicated word problem. And if any of you are going on to general chemistry and organic chemistry, you are going to have to learn how to write out and try things and write your ideas down and not just go straight into the math. Don't just grab that calculator immediately. And that is going to help you in your upper level chemistry courses and probably physics courses and other STEM courses as well. Okay, so this is my math. Feel free to text me if you're lost in what I've done for any section of this. I'm going to go with 2 significant figures here because my mole ratios are counting numbers, they're ratios. They have infinite sig figs, and my molar masses also are given to me, so I should probably be considering them as infinite. So we got 16, let's see, is that right? 1690? I'm gonna double check because I was talking while I was calculating. Okay, 1690.09 grams of CO2. Now, to me, I can see this and go, well, I probably should report this in kilograms because it is on the scale of 10 to the 3. You can leave it like this if your instructor is just asking for mass or asking for grams, but if you really want to start to get to that next level and think, what should I report this in? It would be much easier for someone to understand it if it were in kilograms because it is 10 to the 3. It's, that's actually the definition of kilo, right? So 2 sig figs turning into kilograms would be 1.7 kilograms of carbon dioxide. Or if you wanted to keep it in grams, 1700. So it kind of depends what unit you want to use and what you mean by this information. So if you're trying to scare somebody into, understanding what this means, that for every 500 grams, just grams, half a kilogram of gasoline I put in my car, I get out 1,700, 500 to 1,700. So maybe you want to use this bigger number to communicate that to someone, right? Or maybe you know that they're familiar with the kilogram and how large that is, and going from 500 grams to 1.7 kilograms makes an impact on them. So, you know, your freedom is in your units, especially the higher up you go in science. Okay, that's your first video in stoichiometry in chapter 8 of our course. Please text me if you've got any questions or you need me to go over any of these examples with you.